All right, so I'm going to talk about efficient pack learning from the crowd. This is joint work with Pranjal Wasti, Nika Haghtalab, and Yishai Mansour. As you've probably noticed, I am not Nika Haghtalab. She was unable to attend due to visa issues, so I'm presenting her slides for her. Okay, so think about some standard machine learning problem. For instance, given a bunch of cute furry animals, which of these are some particular species, some particular breed of cat? Okay? And so if you want to do this, you might, say, get some labeled training data, and one way to do that is to crowdsource it. You go on Amazon Turk and you say, you get a bunch of people to label these images for you. Okay, great. So one problem with this is that you know, a lot of people might not know what a Maine Coon cat is. I don't. So, you know, some people will know what it is and others won't. And so you're going to get a lot of noisy responses. And it's not, you know, nice white noise, random classification noise. It's noise that depends on the object. That people know the dog is not one. But, you know, that white cat, could it be? I don't know. Okay? So you're going to get sort of a difficult kind of noise, perhaps. All right. So there's kind of two ways to so standard ways to tackle a problem like this. Right. So one is from the learning point of view. You could say, let's just treat this as a problem of learning from noisy labels. And you know, we have a really good understanding of sample complexity of learning from noisy labels. Runtime, though, we don't have a lot of efficient algorithms for agnostic learning unless we make other assumptions, say, about the distribution. Another approach is to look at the annotation side and say what we really want is to get rid of the noise. So, for instance, let's take majority vote over a bunch of labelers, and hopefully we can do that, and you know, we'll squeeze out the noise by taking big enough majority votes. Okay, so each of these has pluses and minuses. So from the learning algorithm point of view, we really understand the sample complexity. You don't need that many label queries, but the algorithmic problem of finding the best, say, even linear separator with agnostic noise is hard without assumptions on the distribution. On the other hand, from the data annotation perspective, we can just get rid of the noise. We can convert this into an easier learning problem where there's no noise, but we might have to take a bunch of majority votes, and so we're going to use more labeling effort because we're going to have individual objects labeled by a whole bunch of people to do the majority votes. Okay, so what this work is about is trying to combine these together to interleave them in order to get the computational problem as easy as the learning problem without noise, but where the total amount of labeling work has only blown up by a constant factor compared to the case of perfect labelers. And we're going to try to do that through a sort of iterative process. We're going to denoise a few points to learn, a modest error classifier, use that to try to focus our queries on regions that we care about more and try to denoise them. This may sound a bit like boosting, and in fact we're going to be using boosting here. Okay, so here's the formal model and results. So the model is there's some target function out there. You know, is this thing a Maine Coon cat? There's a distribution over unlabeled instances, typical cute furry animals on the web. There's a distribution over labelers, and the assumption is, so here's the assumption, some fraction of them actually know what the target function is. Okay, there's some alpha fraction that actually know what a Maine Coon cat is, and the other 1 minus alpha don't. They have some arbitrary thing in their head. We can think of alpha as, the easier case is when alpha is bigger than a half, like say it's 70%, so 70% actually know the target and 30% are sort of arbitrary. We can also look at the case where alpha is less than a half. Maybe only 30% know what it is and the 70% are arbitrary. In that case, there's an information theoretic problem, which is 70% might think that a Maine Coon cat is a dog, and so you know you're going to get mostly labeled that way. But what we can do is, if we get a small constant number of what we call golden queries, so we're allowed to give an object to really know the answer, to ask someone who knows. We have someone who knows, they're sitting over on the hill, but we can only ask them like 3 questions, all right, a constant number of questions. Then we can do is we can solve this problem. This is called the semi-verified learning model in a recent stock paper of Charakar et al. Okay, and then the theorem is if you have a class, say linear separators, that's efficiently learnable without noise from m samples, we can get an algorithm in this model that will learn from order m labelings efficiently, where every labeler answers only a few questions. You're not allowed to, for example, in this model, find a labeler who knows what a main coon cat is and ask that labeler to label everything. All right? Any given labeler is only, you're not allowed to ask any given one a small number of questions. Okay, and then if alpha is less than a half, then you need a constant number of these golden queries. Okay, so that's the result. Let me just say a few ideas. So let's take the case where there's 70% of them, of the labelers are good and 30% are bad. So first of all, one thing you can do is go for a modest, we're going to do like one round of boosting. So go for a modest error classifier, not error epsilon, error square root of epsilon. You need a lot less data for that. And for that, you can afford to take that smaller amount of data and ask for each one of them, a bunch of people take majority vote, get clean labels, go for it, and get your function. Now that you've got that, you want to do a round of boosting. So what you'd like to do is focus now. So what do we need to do for boosting? We got this f. It's got this modest error rate of square root of epsilon. We now need to focus our distribution, half where it gets it right, half where it gets it wrong. The problem is it's getting most things right. And if you use these labelers, their error rate is higher than this. Okay? So the way to think about this is the ones where f gets it wrong are like needles in a haystack. Okay, so we've got these needles in a haystack, and we need to get a new sample that's half needles, half hay. All right? The hay is easy. It's a haystack. The problem is the needles. Okay? And the problem is these labelers, they're not very good. If you ask for, tell me the needles, most of those things that it thinks they're needles are actually going to be hay. So we need to kind of find these needles. Okay? But without asking too much. And so the technique we use we call probabilistic filtering. So basically, these are the examples coming in. The ones where get incorrect, those are the needles. The ones where it gets correct, those are the hay. We need to ask some questions, and we want the hay to go through with very tiny probability, and the needles should go through with, say, constant probability, so we can get our needles to match with the hay. Okay? So we can run a round of boosting. We're going to do that by doing a majority vote, but here's the way the majority vote's going to work. Given an example, we'll ask one guy, another guy, another guy, another guy. If the majority ever says it's hay, we throw it out. If it stays needle, 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 needle all the way through up to some cutoff point, then we let it through as a needle. Needle meaning that we're getting it wrong. Okay, so the key point here, that what is going to make this work, is about biased random walks. The needles, people are more likely to say are needles. The hay, people are more likely to say is hay. If you have something that's a random walk that's biased 0.7 this way, there's a reasonable chance, if you take a random walk, this is this majority vote, this kind of all prefixes, that random walk never goes below the origin. There's a reasonable chance in the biased random walk that this random walk never goes below the origin. It says needle, 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 this thing goes through. But if it's biased the other way, it's really hay. With very high probability, it will cross. In fact, an expectation cross after only over one steps, and that way we can end up asking not too many questions. Okay, so that's so just to summarize, for dealing with noise in the crowd, we interleave learning and annotating data for best effect. We can get the computational efficiency of no noise learning with a small overhead and number of queries. If alpha is small, like say 30%, here's one trick there. If you ever see an example that splits the world into, say, like 50% say yes, 50% say no, that's a great quiz question. Before you use your labelers, ask them this quiz. First, find the right answer, and if they get that wrong, throw them out. And now you've increased the fraction of the guys left over who actually know the answer. So that's an idea you can use when alpha is small. And that's it. Oh, so the assumption is, because the question is the fraction the same across all examples. Good. So the assumption is, this is really something about the labelers, that some fraction of the labelers actually know the target function. Like 30%, they know what a coon cat is. 70%, they haven't. So they can think, they can be arbitrary. Some think it's a dog, some think it's a raccoon, some think it's any kind of cat.
That's just knowing the main coon cat, right?
Well, that's the target function. So some actually, so one way to think of it is, you have, instead of all your questions, instead of going to a single target function, they're all going to different functions. Some of them are the actual target. Some of them are these arbitrary, crazy things. But you're not allowed to ask any given function more than a constant number of times, because you just want to do it distributed. Yeah.